Before we begin the statically indeterminate beam test, let's go over the key safety measures to keep everyone safe. Students need to wear their lab coat, long pants, jean or work trousers, and also closed-toe shoes, which is mandatory. Okay, first, carefully inspect all equipment. Look for any cracks, rust, or loose parts on the beam, supports, and weights. Okay, next, set up the beam and reaction piers securely. Make sure everything is clamped tight and properly aligned before loading. Add weights gradually and avoid sudden loading. This prevents slipping and ensures accurate reading. Finally, clean up the workspace, return all tools and weights, and leave the area safe for the next user. Remember, good results start with safe practices. Thank you.
Okay, so before we start our experiment, I will introduce to you guys the equipment for this experiment. So first, this is the support frame. It acts as the main structure that holds all the other components in place. It ensures the system remains stable during the experiment. Okay, next, this is the support reaction piers. Each pier is equipped with a load cell to measure the reaction force. So, these piers also act as the support for the beam, and the load cell is located under the beam to measure the vertical reaction force at those points. So, this is the load hanger that we use to put weight or external load onto it, and then we put it into the specific location based on the different scenarios. And for the weight, we use this type of weight, and make sure that you look at the weight level carefully before you put it into your load hanger. So next equipment is the beam. We have 3 different beams to use in this experiment. Each of it have different thickness, and all of it are made of steel. And lastly, this is the measuring tape. It functions to measure the distance accurately along the beam. We need to measure the length of the beam, the position of the supports, and load application points.
So I'll be talking about the methodology of statistically indeterminate beam test, which is the theory behind it. So let's start with the basics. A statistically indeterminate beam is a beam where the number of unknown support reaction is greater than the number of static equilibrium equations available. In simpler terms, we can solve it using statics alone. To find the support reactions, we also need to consider how the beam bends. That means using equation from strength of materials like deflection and compactability equation. In this experiment, we deal with a continuous beam that has 3 supports. When a load is applied, the reaction at the supports are affected not only by the position of and the size of the load, but also how stiff the beam is and how the supports are arranged. This is why we need to account for both an external forces and the internal deformation of the beam. So this is the picture of deflection of the beam. The first one is when the load is applied on the left side, and the second picture is when the load is applied on the right side. So to sum up, the theory behind this methodology combines basic statics with deformation analysis. It's a great example of how mechanical engineering connects forces, material properties, and structural behavior. That's the theoretical side of the methodology. Next, we'll look at the actual experiment and the results we get from it.
So now we move on to the methodology part. First step is to measure the length of the mild steel beam. And then we set it up on the dial gauge. Next step is to take one dial gauge and slide it across to the end. This step is crucial in order to make sure the mild steel beam is leveled properly. So in this step, we must ensure that the needle at both ends points at 0. After that, we take the load hanger and set it up at the calculated length, which is the total length divided by 4. Once the load hangers are set up, we need to make sure that all 3 dial gauges and the needle is pointing at the 0. For the final step, we need to load the hanger with 10 Newton loads sequentially by this order. 10 Newtons on the left, then 20, then 30, After that, we need to read all three gauges in order to determine the forces that are acting on the mild steel beam. We repeat this step for the right hanger also, and after that on both hangers. And lastly, we record the data of the different loads at different locations so we can move on to the next step, which is plotting the graph. And that is all for the methodology part. Thank you.
Okay, guys. So now we will talk about what are the things that we will measure and record it in the statically indeterminate index. Okay, so what the main thing that we are gonna be measured is the support reaction, the beam deflection, and the applied load. So first of all, we will put loads on these two load things here. So first we put 10-0, next is 20-0, and next is 30-0. And for the next experiment, we will put 10-10, 20-20, and then 30-30. So in the next experiment, we will put this here is 0. So 0-10, 0-20, and 0-30.
So next we measure the support force. So we use the dial gauge to calculate the support force, which is located at the left, middle, and the right of the beam. So it is important to zero the dial indicators to make sure the reading is accurate. Lastly, we repeat the experiment by increasing the load at the left side, which is 10 kg to 20 to 30 kg, and we repeat at the right side 10 kg, 20 kg, and 30 kg, and lastly for both of the load hanger, which is 10 kg, 20 kg, and 30 kg.
In the expected result, we predict how the reaction force R1, R2, and R3 will behave under different loading conditions, which is W1 and W2 on each beam. These predictions are based on theoretical calculation using the static equilibrium principles. For beam A, we conducted tests using two load conditions, W1 and W2. The experimental results show how this will influence the support reaction R1, R2, and R3. Similar for beam B, we apply the same loading condition. Reaction force was measured to observe any variation in response compared to beam A. In beam C, we expected a slightly different pattern due to its structural configuration. The data gathered will later be compared to the other beam for analysis. So this is the graph for beam A. This graph shows how the one affect the reaction R1, R2, and R3 in beam. It's plotted with weight on the y-axis and direction on the x-axis to visualize the distribution clearly. So this is the second graph for beam A. Here we see the effect of W2 on the same support reactions. Comparing it with the previous graph help identify load influence individually. So this is the last graph for beam A. This graph displays both W1 and W2 together. It allows us to see the cumulative effect on beam A's reaction. So we move to beam B. This graph displays beam B's reaction to W1. It helps us understand how a different beam design alters support force distribution. Now we observe beam B under W2. We can directly compare this to beam A to check for consistency. So this is the last graph for beam B, which is W1, W2 versus support reaction. And this shows us a complete picture of how beam B handles combined weight just like beam A. So this is the last beam, which is beam C. So it is just same graph before this, which is W1 versus support reaction. So this pattern help us to determine the load's impact on the reaction point. Move to second graph for beam C, which is W2 versus support reactions. This graph capture the differences, reflect structural response variations compared to the other beams, which is beam A and B. Finally, this graph shows the effect of overload on beam C. With this, we can now evaluate performance across all beams under the similar conditions.